Hey students, this is your Nandini ma'am. Today, I'm going to read chapter number 10, Work and Energy of class ninth, and the book is NCERT. So let's get started. In the previous few chapters, we have talked about ways of describing the motion of objects, the cause of motion and gravitation. Another concept that helps us understand and interpret many natural phenomena is work. Closely related to work are energy and power. In this chapter, we shall study these concepts. All living things need food. Living beings have to perform several basic activities to survive. We call such activities life processes. The energy for these processes comes from food. We need energy for other activities like playing, singing, reading, writing, thinking, jumping, cycling, and running. Activities that are strenuous require more energy. Animals too get engaged in activities. For example, they may jump and run. They have to fight, move away from enemies, find food, or find a safe place to live. Also, what we engage some animals to lift weights, carry loads, pull carts, or plow fields. All such activities require energy. Think of machines. List the machines that you have come across. What do they need for their working? Why do some engines require fuel like petrol and diesel? Why do living beings and machines need energy? Work. What is work? There is a difference in the way we use the term work in day-to-day life and the way we use it in science. To make this point clear, let us consider a few examples. Not much work in spite of working hard. Kamali is preparing for examinations. She spends a lot of time in studies. She reads books, draws diagrams, organizes her thoughts, collects question papers, attends classes, discusses problems with her friends, and performs experiments. She expends a lot of energy on these activities. In common parlance, she is working hard. All this hard work may involve very little work if we go by the scientific definition of work. You are working hard to push a huge rock. Let us say the rock does not move despite all the effort. You get completely exhausted. However, you have not done any work on the rock as there is no displacement of the rock. You stand still for a few minutes with a heavy load on your head. You get tired. You have exerted yourself and have spent quite a bit of your energy. Are you doing work on the load? The way we understand the term work in science, work is not done. You climb up the steps of a staircase and reach the second floor of a building just to see the landscape from there. You may even climb a tall tree. If we apply the scientific definition, these activities involve a lot of work. In day to day life, we consider any useful physical or mental labor as work. Activities like playing in a field, talking with friends, humming a tune, watching a movie, attending a function are sometimes not considered to be work. What constitutes work depends on the way we define it. We use and define the term work differently in science. To understand this, let us do the following activities. Activity 10.1. We have discussed in the above paragraphs a number of activities which we normally consider to be work in day to day life. For each of these activities, ask the following questions and answer them. What is the work being done on? What is happening to the object? Who or what is doing the work? Scientific conception of work. To understand the way we view work and define work from the point of view of science, let us consider some situations. Push a pebble lying on a surface. The pebble moves through a distance. You exerted a force on the pebble and the pebble got displaced. In this situation, work is done. A girl pulls a trolley and the trolley moves through a distance. The girl has exerted a force on the trolley and it is displaced. Therefore, work is done. Lift a book through a height. To do this, you must apply a force. The book rises up. There is a force applied on the book and the book has moved. Hence, work is done. A closer look at the above situations reveals that two conditions need to be satisfied for work to be done. A force should act on an object and the object must be displaced. If any one of the above conditions does not exist, work is not done. This is the way we view work in science. A bullock is pulling a cart. The cart moves. There is a force on the cart and the cart has moved. Do you think that work is done in this situation? Activity 10.2. Think of some situations from your daily life involving work. List them. Discuss with your friends whether work is being done in each situation. Try to reason out your response. If work is done, which is the force acting on the object? What is the object on which the work is done? What happens to the object on which work is done? Activity 10.3. Think of situations when the object is not displaced in spite of a force acting on it. Also, think of situations when an object gets displaced in the absence of a force acting on it. List all the situations that you can think of for each. Discuss with your friends whether work is done in these situations. Work done by a constant force. How is work defined in science? To understand this, we shall first consider the case when the force is acting in the direction of displacement. Let a constant force F act on an object. Let the object be displaced through a distance S in the direction of the force. Let W be the work done. We define work to be equal to the product of the force and displacement. So work done is equal to force multiplied by displacement. W is equal to Fs. Thus, work done by a force acting on an object is equal to the magnitude of the force multiplied by the distance moved in the direction of the force. Work has only magnitude and no direction. In equation 10.1, if force is 1 Newton and S is 1 meter, then the work done by the force will be 1 Newton meter. Here, the unit of work is Newton meter or joule. Thus, 1 joule is the amount of work done on an object when a force of 1 Newton displaces it by 1 meter along the line of action of the force. Look at equation 10.1 carefully. What is the work done if the force on the object is 0? What would be the work done when the displacement of the object is 0? Refer to the conditions that are to be satisfied to say that work is done. Consider another situation in which the force and the displacement are in the same direction. A baby pulling a toy car parallel to the ground as shown in figure 10.4. The baby has exerted a force in the direction of the displacement of the car. In this situation, the work done will be equal to the product of the force and displacement. In such situations, the work done by the force is taken as positive. Consider a situation in which an object is moving with a uniform velocity along a particular direction. Now a retarding force F is applied in the opposite direction. That is, the angle between the two directions is 180 degrees. Let the object stop after a displacement S. In such a situation, the work done by the force F is taken as negative and denoted by the minus sign. The work done by the force is F into minus S or minus F into S. It is clear from the above discussion that the work done by a force can be either positive or negative. To understand this, let us do the following activity. Activity 10.4. Lift an object up. Work is done by the force exerted by you on the object. The object moves upwards. The force you exerted is in the direction of displacement. However, there is the force of gravity acting on the object. Which one of these forces is doing positive work? Which one is doing negative work? Give reasons. Work done is negative when the force acts opposite to the direction of displacement. Work done is positive when the force is in the direction of displacement. Energy. Life is impossible without energy. The demand for energy is ever increasing. Where do we get energy from? The sun is the biggest natural source of energy to us. Many of our energy sources are derived from the sun. We can also get energy from the nuclei of atoms, the interior of the earth, and the tides. Can you think of other sources of energy? Activity 10.5. A few sources of energy are listed above. There are many other sources of energy. List them. Discuss in small groups how certain sources of energy are due to the sun. Are there sources of energy which are not due to the sun? The word energy is very often used in our daily life, but in science, we give it a definite and precise meaning. Let us consider the following examples. When a fast moving cricket ball hits a stationary wicket, the wicket is thrown away. Similarly, an object, when raised to a certain height, gets the capability to do work. You must have seen that when a raised hammer falls on a nail placed on a piece of wood, it drives the nail into the wood. We have also observed children winding a toy, such as a toy car, and when the toy is placed on the floor, it starts moving. When a balloon is filled with air and we press it, we notice a change in its shape. As long as we press it gently, it can come back to its original shape when the force is withdrawn. However, if we press the balloon hard, it can even explode, producing a blasting sound. In all these examples, the objects acquire through different means the capability of doing work. An object having a capability to do work is said to possess energy. The object which does the work loses energy, and the object on which the work is done gains energy. How does an object with energy do work? An object that possesses energy can exert a force on another object. When this happens, energy is transferred from the former to the latter. The second object may move as it receives energy and therefore do some work. Thus, the first object had a capacity to do work. This implies that any object that possesses energy can do work. The energy possessed by an object is thus measured in terms of its capacity of doing work. The unit of energy is therefore the same as that of the work, that is joule. 1 joule is the energy required to do 1 joule of work. Sometimes a larger unit of energy called kilojoule is used. 1 kilojoule equals 1000 joules. Forms of energy. Luckily, the world we live in provides energy in many different forms. Various forms include mechanical energy, potential energy plus kinetic energy, heat energy, chemical energy, electrical energy, and light energy. Think it over. How do you know that some entity is a form of energy? Discuss with your friends and teachers. James Prescott Joule was an outstanding British physicist. He is best known for his research in electricity and thermodynamics. Amongst other things, he formulated a law for the heating effect of electric current. He also verified experimentally the law of conservation of energy and discovered the value of the mechanical equivalent of heat. The unit of energy and work called joule is named after him. Kinetic energy. Activity 10.6. Take a heavy ball, drop it on a thick bed of sand. A wet band of sand would be better. Drop the ball on the sand bed from height of about 25 centimeter. The ball creates a depression. Repeat this activity from heights of 50 centimeter, 1 meter, and 1.5 meter. Ensure that all the depressions are distinctly visible. Mark the depressions to indicate the height from which the ball was dropped. Compare their depths. Which one of them is deepest? Which one of them is shallowest? Why? What has caused the ball to make a deeper dent? Discuss and analyze. Activity 10.7. Set up the apparatus as shown in figure 10.5. Place a wooden block of known mass in front of the trolley at a convenient fixed distance. Place a known mass on the pan so that the trolley starts moving. The trolley moves forward and hits the wooden block. Fix a stop on the table in such a manner that the trolley stops after hitting the block. The block gets displaced. Note down the displacement of the block. This means work is done on the block by the trolley as the block has gained energy. From where does this energy come? Repeat this activity by increasing the mass on the pan. In which case is the displacement more? In which case is the work done more? In this activity, the moving trolley does work and hence it possesses energy. A moving object can do work. An object moving faster can do more work than an identical object moving relatively slow. A moving bullet, blowing wind, a rotating wheel, a speeding stone can do work. How does a bullet pierce the target? How does the wind move the blades of a windmill? Objects in motion possess energy, and we call this energy kinetic energy. A falling coconut, a speeding car, a rolling stone, a flying aircraft, flowing water, blowing wind, a running athlete, etc. possess kinetic energy. In short, kinetic energy is the energy possessed by an object due to its motion. The kinetic energy of an object increases with its speed. How much energy is possessed by a moving body by virtue of its motion? By definition, we say that the kinetic energy of a body moving with a certain velocity is equal to the work done on it to make it acquire that velocity. Let us now express the kinetic energy of an object in the form of an equation. Consider an object of mass m moving with a uniform velocity u. Let it now be displaced through a distance s when a constant force F acts on it in the direction of its displacement. From equation 10.1, the work done W is Fs. The work done on the object will cause a change in its velocity. Let its velocity change from u to v, and let A be the acceleration produced. We studied three equations of motion. The relation connecting the initial velocity and the final velocity of an object moving with a uniform acceleration a and the displacement s is v square minus u square is equal to 2as. This gives s is equal to v square minus u square over 2a. From section 9.4, we know F is equal to ma. Thus, using equation 10.2 in equation 10.1, we can write the work done by the force F as W is equal to m into A into V square minus U square over 2A, or W is equal to half m into V square minus U square. If the object is starting from its stationary position, that is U is 0, then W is equal to half mv square. It is clear that the work done is equal to the change in the kinetic energy of an object. If U is 0, the work done will be half mv square. Thus, the kinetic energy possessed by an object of mass m and moving with a uniform velocity v is Ek is equal to half mv square. Potential energy. Activity 10.8. Take a rubber band, hold it at one end and pull the other. The band stretches. Release the band at one of the ends. What happens? The band will tend to regain its original length. Obviously, the band had acquired energy in its stretch position. How did it acquire energy when stretched? Activity 10.9. Take a slinky as shown below. Ask a friend to hold one of its ends. You hold the other end and move away from your friend. Now you release the slinky. What happened? How did the slinky acquire energy when stretched? Would the slinky acquire energy when it is compressed? Activity 10.10. Take a toy car, wind it using its key, place the car on the ground. Did it move? From where did it acquire energy? Does the energy acquired depend on the number of windings? How can you test this? Activity 10.11. Lift an object through a certain height. The object can now do work. It begins to fall when released. This implies that it has acquired some energy. If raised to a greater height, it can do more work and hence possesses more energy. From where did it get the energy? Think and discuss. In the above situations, the energy gets stored due to the work done on the object. The energy transferred to an object is stored as potential energy if it is not used to cause a change in the velocity or speed of the object. You transfer energy when you stretch a rubber band. The energy transferred to the band is its potential energy. You do work while winding the key of a toy car. The energy transferred to the spring inside is stored as potential energy. The potential energy possessed by the object is the energy possessed or present in it by virtue of its position or configuration. Activity 10.12. Take a bamboo stick and place a bow as shown in figure 10.6. Place an arrow made of a light stick on it with one end supported by the stretch string. Now stretch the string and release the arrow. Notice the arrow flying off the bow. Notice the change in the shape of the bow. The potential energy stored in the bow due to the change in the shape is thus used in the form of kinetic energy in throwing off the arrow. Potential energy of an object at a height. An object increases its energy when raised through a height. This is because work is done on it against gravity while it is being raised. The energy present in such an object is the gravitational potential energy. The gravitational potential energy of an object at a point above the ground is defined as the work done in raising it from the ground to that point against gravity. It is easy to arrive at an expression for the gravitational potential energy of an object at a height. Consider an object of mass m. Let it be raised through a height h from the ground. A force is required to do this. The minimum force required to raise the object is equal to the weight of the object mg. The object gains energy equal to the work done on it. Let the work done on the object against gravity be W. So, work done W is equal to force into displacement, which is mg into h, and W is equal to mgh. Since work done on the object is equal to mgh and energy equal to mgh units is gained by the object. This is the potential energy of the object. So, EP is equal to mgh. The potential energy of an object at a height depends on the ground level or the zero level you choose. An object in a given position can have a certain potential energy with respect to one level and a different value of potential energy with respect to another level. It is useful to note that the work done by the gravity depends on the difference in vertical heights of the initial and final positions of the object and not on the path along which the object is moved. Figure 10.8 shows a case where a block is raised from position A to B by taking two different paths. Let the height AB is equal to h. In both the situations, the work done on the object is mgh. Are various energy forms interconvertible? Can we convert energy from one form to another? We find in nature a number of instances of conversion of energy from one form to another. Activity 10.13. Sit in small groups, discuss the various ways of energy conversion in nature. Discuss the following questions in your group. How do green plants produce food? Where do they get their energy from? Why does the air move from one place to another? How are fuels such as coal and petroleum formed? What kinds of energy conversion sustain the water cycle? Activity 10.14. Many of the human activities and the gadgets we use involve conversion of energy from one form to another. Make a list of such activities and gadgets. Identify in each activity or gadget the kind of energy conversion that takes place. Law of conservation of energy. In activities 10.13 and 10.14, we learned that the form of energy can be changed from one form to another. What happens to the total energy of a system during and after the process? Whenever energy gets transformed, the total energy remains unchanged. This is the law of conservation of energy. According to this law, energy can only be converted from one form to another. It can neither be created nor destroyed. The total energy before and after the transformation remains the same. The law of conservation of energy is valid in all situations and for all kinds of transformations. Consider a simple example. Let an object of mass m be made to fall freely from a height h. At the start, the potential energy is mgh and kinetic energy is 0. Why is the kinetic energy 0? It is 0 because its velocity is 0. The total energy of the object is thus mgh. As it falls, its potential energy will change into kinetic energy, and if v is the velocity of the object at a given instant, the kinetic energy would be half mv square. As the fall of the object continues, the potential energy will decrease while the kinetic energy would increase. When the object is about to reach the ground, h is equal to 0 and v will be the highest. Therefore, the kinetic energy would be the largest and the potential energy the least. However, the sum of the potential energy and kinetic energy of the object would be the same at all points. That is, potential energy plus kinetic energy is equal to constant, or mgh plus half mv square is equal to constant. The sum of the kinetic energy and potential energy of an object is its total mechanical energy. We find that during the free fall of the object, the decrease in potential energy at any point in its path appears as an equal amount of increase in kinetic energy. Here, the effect of air resistance on the motion of the object has been ignored. There is thus a continual transformation of gravitational potential energy into kinetic energy. Activity 10.15. An object of mass 20 kg is dropped from a height of 4 meters. Fill in the blanks in the following table by computing the potential energy and kinetic energy in each case. For simplifying the calculations, take the value of g as 10 meter per second square. What would have happened if nature had not allowed the transformation of energy? There is a view that life could not have been possible without transformation of energy. Do you agree with this? Rate of doing work. Do all of us work at the same rate? Do machines consume or transfer energy at the same rate? Agents that transfer energy to do work at different rates. Let us understand this from the following activity. Activity 10.16. Consider two children, say A and B. Let us say they weigh the same. Both start climbing up a rock separately. Both reach a height of 8 meters. Let us say A takes 15 seconds while B takes 20 seconds to accomplish the task. What is the work done by each? The work done is the same. However, A has taken less time than B to do the work. So, who has done more work in a given time? Say in 1 second. A stronger person may do certain work in relatively less time. A more powerful vehicle would complete a journey in a shorter period of time than a less powerful one. We talk of the power of machines like motorbikes, motor cars. The speed with which these vehicles change energy or do work is a basis for their classification. Power measures the speed of work done, that is, how fast or slow work is done. Power is defined as the rate of doing work or rate of transfer of energy. If an agent does a work W in time T, then power is given by power is equal to W over T. The unit of power is watt, having the symbol W. So 1 watt is the power of an agent which does work at the rate of 1 joule per second. We can also say that power is 1 watt when the rate of consumption of energy is 1 joule per second. We express larger rates of energy transfer in kilowatts. The power of an agent may vary with time. This means that agent may be doing work at different rates at different intervals of time. Therefore, the concept of average power is useful. We obtain average power by dividing the total energy consumed by the total time taken. Activity 10.17. Take a close look at the electric meter installed in your house. Observe its features carefully. Take the readings of the meter each day at 6:30 a.m. and 6:30 p.m. Do this activity for about a week. How many units are consumed during daytime? How many units are used during night? Tabulate your observations. Draw inferences from the data. Compare your observations with details given in the monthly electricity bill. What you have learned. Work done on an object is defined as the magnitude of the force applied multiplied by the distance moved by the object in the direction of the applied force. The unit of work is joule. 1 joule is equal to 1 Newton into 1 meter. Work done on an object by a force would be zero if the displacement of the object is zero. An object having capability to do work is said to possess energy. Energy has the same unit as that of work. An object in motion possesses what is known as kinetic energy of the object. An object of mass m moving with velocity v has a kinetic energy of half mv square. The energy possessed by a body due to its change in its position or shape is called the potential energy. The gravitational potential energy of an object of mass m raised through height h from the Earth's surface is given by mgh. According to the law of conservation of energy, energy can only be transformed from one form to another. It can neither be created nor destroyed. The total energy before and after the transformation always remains constant. The energy exists in nature in several forms, such as kinetic energy, potential energy, heat energy, chemical energy, etc. The sum of the kinetic and potential energies of an object is called its mechanical energy. Power is defined as the rate of doing work. The SI unit of power is watt. 1 watt is equal to 1 joule per second. So this was the chapter. Happy listening to the chapter. Thank you.